general rational number, what will you do? F of n by n into n is f of n, which is n f of 1. At the same time, this is n f of n by n. F of n by n is n by n times f1. Very good. All of you know this symbol, right? Stands for rational numbers. For all rational numbers, you have this. Sorry. Right. So now next thing is that we want something from x and r. We have only got the rational numbers, right? We now want something for the irrational ones. So here are some bad news for you. You cannot prove this for all the numbers. I'll very soon show you why. Consider the function f of x equal to x if x is less. Take this function. What I did was that for all rational multiples of root 2, so root 2 root 2, minus 2 by 3 root 2, minus 5 by 7 root 2. For all rational multiples of root 2, I define f to be 5x. And for all other numbers, I define it to be x. You can check that this function also satisfies. Can anyone tell me why? So just think of the process of how did we go from rational numbers. So we started with 1, right? Then 1 plus 1 plus 1 plus 1 plus 1, all integers are done. Then you divide one integer with another integer, you get all rational numbers. Right? You see, I can do the same thing with root 2, right? F of 4 root 2 by 5. What is it? 4 by 5 times f of root 2. Do you see why this is the case? Do you all see that this is the case? Everything that I did with 1, I will now do with root 2. So for all rational numbers of root 2, I'll get that it is, so for basically, I get that f of qx is q of f of x. Where q is rational and x is any number. What you did with 1, you do with x. Right? Now the problem is that root 2 is not rational, right? So root 2 does not talk with any rational numbers. You cannot derive a contradiction by saying that, oh, for rational numbers you have x, but for like rational multiples of root 2 you have 5x. They will never talk to each other. You will never be able to add combinations of them and add combinations of root 2 and get some rational number. Non-zero rational, right? They will never talk to each other. So I can do stuff like this. Right? So that's where Cauchy's equation stops.
Is applicable for only rational.
Okay, so let me clarify things.
Is there any rational number for this?
Is there any irrational number for which what happens?
For which this Cauchy
So you are mistaking this. So if I have a function from f of q to r such that f of x plus y equals to f of x plus f of y, then I have fx equals to x f1, no question marks. We just derived it, right? This is the only function which satisfies this. All I'm saying is that if you have a function f r to r such that f of x plus y equals to f of x plus f of y, this function satisfies this too. But if your domain is R, then this is no longer the only function which satisfies this. As I gave you the 5x and x example, that function satisfies this equation. You can verify that. So, and Further discussion of this will actually take me to undergraduate mathematics. Uh, Turns out that this is the only solution if you take f to be continuous. But continuity is a concept from calculus and they will never ask it in an Olympiad question. And in particular, many people assume continuity and do write stuff. You will get zero mark if you put in an Olympiad. Olympiad is supposed to be elementary, right? But so why did I cover something which we call undergraduate mathematics? This precisely to show you that at least for rational numbers you can say this. Maybe not for all real numbers, but at least for the rational numbers you can say this. Is this clear to all of you? Is this clear? So this is the main takeaway. That is, n is a function such that f of x plus y equals fx plus fy. Then you have this, and you cannot say anything more than that in general. Okay. This is the first thing. So this might, and this is typically not the flavor of Olympiad uh, functional equations are like. Olympiad functional equations mostly you can solve completely. Uh, but nevertheless, this trick was very important. That's why I told it. Now I come to another very classic equation, which is known as Jensen's equation. You must have heard of Jensen's inequality. So Jensen's equality. Uh, is 2f of x plus y by 2. Is this question clear? You have to find all functions which take as input rational numbers, give as output any real number, and will satisfy this equation for all x1 input. Is this clear? Once again, can you give me some, solutions to this just by seeing this equation? F of x equals x. Will f of x equals to 2x fall? Will f of x equals to kx fall here? Why not? Kx plus ky 2k x plus y by 2. Aren't these two things equal? F is equal to kx works, right? Just need okay. If there is any discomfort, please do let me know. Fx equal to kx works, right? Thus fx equal to kx plus 23 work. Please check. Does this work? Does it work or not? Fx equal to kx plus 23.
Yes, yes.
Right, because you have plus 23 here, plus 23 here, and you have 2 times 23 here. Works, right? So just by so in functional equations you must develop this ability to just guess the solution just by seeing this equation. So what are the solutions to this? Fx equals to ax plus b. We do not know if there are other solutions, but fx equals to ax plus b is certainly a solution, right? Is this clear? Where a, b are any real numbers. Okay, so now how do you actually go about proving this? So here I have got a second trick, which is known as shifting. So what was the takeaway from Cauchy? How you can get to rational numbers from integers. That was our main takeaway from Cauchy. What will be our main takeaway from Jensen? Shifting. What do I mean by shifting? Acha, can you express B in terms of f? What is B? F of 0, right? And leave A as it is. You see, carrying a constant around is a bit of a headache, right? What I do is that I'll create a new function gx, which is fx minus f0. I shifted fx by f0. Can you tell me what g0 is? 0. This is precisely why I shifted. You know, we saw one example of shifting in the last class also. What was that example?
By
PA equal to PB equal to PC equal to PD equal to 5 and PBA. We shifted by 5. Why do you shift? So that you can make as many things 0 as possible. The G0 equal to 0 is certainly a nice thing to look at. Now, what is fx? Gx plus f0. So this is gx plus f0. What is fy?
by
Gy plus f0. What is f of x plus y by 2? G of x plus y by 2 plus g0. Sorry. So what do we get? Then Gx also satisfies Jensen's equation. But now we have an extra advantage. What is that advantage? We know G0 equals 0. In the earlier equation, we derived that f0 equals to 0. Here we did not have that. In fact, if you put x equal to y equal to 0, you will get 2f0 equal to 2f0. You will get like, trivial stuff, right? So when you get trivial stuff like this, you should usually try to apply shifting so that you get something like G0 equal to 0. Okay, so now we kind of like force G0 to 0 by Pf. So we have Gx plus Gy equal to 2Gx plus y by 2, and we also have G0 equal to 0. Right. So this was a main example of shifting. Now you have to manipulate. So I'll tell you some standard recipes for manipulation. The first, the most obvious and stupid one is put everything 0. Second one is put one of the variables 0, leave the other one 3. Okay, so let's put y equal to 0 and let's leave x as it is. So what do we get? Gx plus g0 equal to what? 2gx by 2. Right. What is g0? So what do we get? Gx equal to 2gx by 2. This is a nice thing to do. So what do we know until now? G0 equal to 0. G2x equal to 2gx. These are the two things that we know. What if G2x equal to 2gx? What is 2gx plus y by 2?
GX.
What do you get? G actually satisfies Cauchy. So what does that mean? And the codomain of G is Q. So G is a function with domain rational numbers and it satisfies the Cauchy equation. So what do we get? Gx equal to what? Xg1, which implies fx equal to what? Xg1 plus f0. Right. Now you see G1 and f0 are constants. So write this as A, write this as B, that is good. And now you should finally check that Ax plus B indeed satisfies this equation. So what are all the solutions of this functional equation? Fx equals Ax plus B. Is this clear? Okay. So I will now give an Olympiad college chain more 2020. Find all functions such that f of x plus f of t equals f of y plus f of z, where x plus y is y is t are an x. So for the earlier two equations, we had a functional equation which was satisfied by all possible inputs. Now our functional equation is satisfied only by a special set of inputs. The inputs must be of this form: x less than y less than z less than t, and x y z t are an input. Once again, uh, you see, similar to Jensen's equation, if I add fx, if I add 23 here and 23 here, basically what I'm saying is if f satisfies this, f plus 23 also satisfies this. Right? So when you have a functional equation where you can shift the function and the function still satisfies the equation, what should you do? What should you do? Shifting, right? So what will now g0 equal to 0, g and gx will also satisfy this, right? Without loss of generality, what can we assume? Okay. So basically you shift the whole thing and then you have gx plus gt equals to gy plus gc. Right. With the added benefit that g0 equals 0. So this is one trick. After that there are uh, after that the key to functional equations which you must realize is that you must keep putting various inputs and see what you get. After you have filled pages of calculations, eventually you will see something. But there is no method to functional equations process. You just have to keep putting various inputs. So what is one technique that we learned in the last question? That if possible, try to make many things zero. Right. So what I do is I make y zero. Why do I make y zero? Well, actually I solved this question on my own. I saw that y equal to 0 will lead somewhere. That's why I'm telling you. When you are solving this question on your own in the exam, you won't know that. That's why I said, right, you must do pages of calculation. Eventually, you will see that some things will start working. So when I say that y equal to 0, put y equal to 0, it is because I have worked out the question on my own and I saw that this led somewhere. That's why I'm doing this. Okay, so I put y equal to 0, but given that we need x, y, z to be in an AP, right? So we have an AP, we still have to fill something, right? Uh, so suppose I put this as x. Can you fill in the other two parts of the AP for me? First of all, we have negative x upon b. Just I'm confused. So what is this term? A by 2. And what is this term? Negative a by 2. And here I have to ensure that p not equal to 0 because they are strictly basically t greater than 0. So this is strictly against. If you put this, what do you get? G of minus t by 2 plus gt equal to g0, which is 0. G of t by 2. No, here we have minus t, right? No, there is no Cauchy's theorem. Because something that worked in that case. Here you have to, if you want to say that g of minus t by 2 is minus gt by 2, you have to prove it. So there are, it was not Cauchy's theorem. For a specific functional equation, we have that, sure. But for this, you can't say that now. So I have already written this down and I erase it. The functional equation itself. This is one equation that you have, right? Now you see, it would be nice if we had what we wanted, right? G of minus t is minus g2, right? So how do you get that in R framework? Just reverse the equation. Now you take the AP minus t by 2, 0 and t by 2. You take this AP. This is also an AP, right? What do you get? The sum of the g's of this two, g of minus t plus g of t by 2 is g of minus t by 2. Right? So what do you get? G of minus t by 2 is g of t by 2 plus g of minus t. Now do you see something? G of minus t is minus g. T greater than t. So you basically get what you wanted, but you have to prove it. You do not. There is no Cauchy's theorem which tells you that. You have to prove it. We proved it, right? So this is good. We have something. Now you see, and another classic sign that Cauchy is involved somewhere is if I give you that the domain of the function is Q. Because as you see, most functional equations are from functions from R to R. So if I give you a function which is from Z or from Q, then it's a very good sign that maybe Cauchy is involved somewhere. So if you have to apply Cauchy, what is the first thing that you have to find out? You have to first solve the equation from integers. Okay, so this is an AP. G of minus 1 plus G of 2 is G of 0, which is 0, is G of 1. What is G of minus 1? Minus G of 1. So what is G of 2? 2G1. Then you take the AP 0, 1, 2, 3. What do you get? G of 0 plus G of 3 equal to G of 1 plus G of 2. G of 2 is 2, G of 1, so this is 3 G of 4.
It is satisfied.
So now can we say that G of n equal to n G of 1? For all n integers?
And it is a rational number to make it. Rational number. If you have a single number, I will take rational number to that it is satisfied.
Okay, so then basically the next step is to take rational numbers and prove that gx equal to xg1. And then finally you have to shift back. You see fx was gx minus g0. So what do you get? Fx is now ax plus b. This Cauchy part I'll leave for you to do. I'll now move to, and so this you can read as homework. The Cauchy part, extending the Cauchy part I'll give to you. You see that in Cauchy you would have directly written f of omega plus omega plus omega plus omega equal to 5 of f of omega. You don't have that here, but you will get that. So like we have to work hard to get this. Similarly, you will have to do some more, manipulations yourself to get that. Once you get that, then you can do the same Cauchy process to get that fx equal to xf1 for all rationals. So that I leave for you to do. So the next question, the next question is quite tough. So it was in the, if I remember correctly, it was in the National Olympiad of Kazakhstan. And Kazakhstan might seem funny to you. They do good math. So for this question, I will ask you to derive various things, and basically because I wanted to do some of the manipulations yourself. Because functional equations is best learned when you do the manipulations yourself. So, first, what is the first instinct? What is what is the first thing you should do when you see an equation like this?
Zero.
X equal to y equal to 0. Okay. So now this is a very ugly thing. You did not get anything about f0. You have f0 square plus f0 inside. Right? Now what do you do? In the previous cases, we either got f0 equal to 0 or we got that f0 can be anything, so you shift it, right? Now you have this very specific weird expression from which f is 0. What do you do? Sorry?
We take epsilon common.
Okay, you can, but other than that, So another trick, which is really a trick because there is nothing really mathematical to it, is that when we see expressions like this, we start to oh, can we take this long, can we do that, right? So sometimes we get so involved in the expression that we miss the larger picture. So when you get something complicated like this, put u equal to f0 square plus f0. You might say that this is a stupid step, right? Just replace this. But the thing is that I can now put u somewhere here to get to see if I get something, right? Otherwise, if I say that put x equal to f0 square plus f0, you have so many f's here that you kind of get lost what the whole thing was, right? But now that I've made this variable substitution, you have a psychological comfort that okay, we have f equal to 0 for some u. We don't particularly care what that u is, but it's for some u. Okay. Now that you have f equal to 0, what's the most natural thing that you want to do? Right? You can never take fx equal to, you can always ensure that x is equal to something. You can never force fx to be something. F is 0, right? So you take x equal to f is basically x equal to 0.
You can put x equal to y equal to u.
Yes, you can put x equal to y equal to u. But once again, since I've solved that question myself, I'll ask you just to put x equal to u. What do you do? What? Sorry? Put x equal to u. What do you get?
F of y equal to y.
Sorry? How do you get f of y equals to 1? You get f of y equal to 1, right? This is f of y. F square, this will become 0, so you get f of y. F will become 0, so f of y equals 1, right? Is this clear? So now, once again, like Cauchy and Jensen, this will have a very special name. It's called an involution. So functions will satisfy f of y equal to y for all y, for every input. They are known as involutory functions, or this is known as an involution. Involution basically means that if you apply the same function twice, you get back what you had. So before I proceed any further, uh, I'll ask you, do you know what an injective function is? Injective function? One, yeah. I can never remember one and also other. Injective, subjective, and bijective. Do you know what these things are? Injective, subjective. Okay. So let f from A to B be a function. A, B can be any size. We say f is injective if f of x equal to f of y implies x equal to y. Which means that if your function is giving the same output for two inputs, then the inputs must have been the same. So is x cube an injective function? Is x cube an injective function? X cube from R to R. Is x square an injective function? Why not?
Plus minus 1 will be the same.
X square is not injective. Why? Because 1 and minus 1 will give the same output, despite being different. So what does injective mean? That different inputs give different outputs. So the contrapositive, you know what a contrapositive is, right? If you don't bother, can you see that these things are the same, saying the same? Fx equal to fy implies x equals to y. Alternatively, x not equal to y implies fx not equal to fy. So if f satisfies this for all xy, then we call f injective. F is surjective if for all b in B, there exists A in A such that fa equals b. What does this mean? What does this mean? Basically, for every number, every element in the codomain, there is an element in the domain which gets mapped to that number. Is this subjective? Is this subjective? A function from R to R where x is mapped to x square. Is this subjective?
Not subjective.
Why not?
Because negative numbers can't appear.
Because there is no real number whose square is minus 1, right? This is not subjective. F R to R greater than or equal to 0, fx equal to x square. Is this subjective? Why? Because every positive real number has something which is a square. Right? Basically, for every r in r greater than or equal to 0, you have f of root r equal to r. Right? So, so you see, basically, whether a function is surjective depends on what the codomain is. The same function, when I change the codomain, it became surjective. F is bijective if f is injective and subjective. So what does bijective mean? I mean, like, okay, it's injective and subjective, but what does it mean in terms of functions? Sorry? That is a bisection, but that is not the only bisection. Basically, suppose you have a function. Is this function injective? This function is not injective, right? Is this function injective? Okay. Is this function injective?
Yes.
Is it subjective?
No.
What should I do to make it subjective?
One more.
I should remove this extra point here. Now it becomes, now it is subjective and injective also. So this is a function which is bijective. So basically, what does bijective mean? That for every element in the codomain, there is a unique element in the domain which gets mapped to it. Subjective merely says that there should be something in the domain which gets mapped. Bijective says there should be a unique element, exactly one element which should get mapped. So for example, is this bijective? Is this bijective? How do you check if a function is bijective or not? First, is it injective?
Yes.
You see, I've changed the domain. Now the domain is just the positive real numbers. If you have trouble understanding this notation, it's zero to
Yes, it is. Yes, it is.
it's bijective, it's injective, right? Because no two positive real numbers can have the same square. Is it subjective? Why? Because for any r in this or root r in this you have. So because it is injective and subjective, it is bijective. Okay. So the reason I told you all this is because let f r to r be a function such that f of y equals f y. Prove that f is bijective. So when I ask you to prove that a function is bijective, what's the first thing that you need to prove? It's injective, right? What's the condition of injectivity? Fx equal to fy.
And it's equal to 1.
If we can prove this, then we would have shown that f is injective, right? Now you see if fx equal to fy, then f of x equal to f of y.
Equal to 1.
What is f of x?
X.
What is f of y?
1.
So fx equal to fy implies x equal to 1. So f is injective. F is subjective also. Can anyone see why?
What's that? Please.
Can somebody see why f is subjective? What does subjectivity mean? That for any real number, there should be some other real number which gets mapped to it. So let y be any real number. Can you tell me a number here which gets mapped to y? F of y, right? F of y equals y, right? So for every real number y, f of y gets mapped to y. So f is subjective also, which means that f is. So why do we care so much about bijectivity? Care about bijectivity because bijective functions have properly defined inverses. Basically, if you have a function like this, can you define an inverse of this function? You can't, right? Because where will you send this element? Here or here? So the first condition of inverse for an inverse to exist is that the function should be injective. Because if it is not injective, you do not have, you know, you cannot decide where to send this. Can you invert this function? Why not? Because where will you send this, right? So you can't invert it either. But for a bijective function, so this is a bijective function. How will you invert this function? Revert all the arrows. That's the inverse. So for example, f from R to R x cube is a bijective function. Right. What's the inverse? cube root x. You see that's why x squared does not have an inverse over all of r because x square is not injected. That's why we always say we should take a positive root because x square is an inverse only when you view it over the positive real numbers. Okay, so all this lecture was to emphasize that if you ever get a question of this form, you have a very powerful property in your hands, namely that f is bijective. Okay, so let us return to our original equation. What was it? Right. But now, what do we know? We know that there exists a u such that f u equal to 0. We also know that f is bijective. Okay, this is nice, but how do I actually use it? Okay. Right. Because f is bijective, I can write fx plus fy equal to f inverse of x and x plus y. But that is not help. We use involution again. You see, normally for not basically when you have a functional equation, you can always do stuff like put x equal to ft, right? But normally things like this only complicate your things because you get nested functions f of f of f of f of x something, right? But when your function is involutive, this is actually good. Why? Because if your function nests an even number of times, it basically annihilates itself. And if it nests an odd number of times, it becomes just f. So when you have involution in your hands, and suppose I want to kill this. I want to, instead of fx, I want to make it a variable which I can control. What should I do? Put x equal to f of t, right? T is something I can control. I'll put f of t here. This will become just t square. So x is ft. What is f of t? T, right? And y remains y. Now what is tft plus y?
X.
F of ft square plus f, right? Just put x equal to t. tft plus y is f of ft square plus f, right? Right. So what do you get? F of t square plus fy is f of ft square plus fy. F is bijective. In particular, it is injective. When you have an injective function, what can you do? If f of input 1 is equal to f of input 2, what do we have?
Input 1 is equal to input 2.
What do we get from here? So what is f of t? Plus minus 2. Are we done? And you can indeed verify that if I put fx equal to x here, it's very clearly satisfied. If I put fx equal to minus x, this is also satisfied. Why? Because fx equal to minus x squared still becomes x. Y becomes minus y. F of this is becomes y minus x squared. Fx is minus x, which is minus x squared, which is y. See these two things are equal, right? So fx equal to x, then fx equal to minus x are the solutions, right? We have got that. Huh? Are we done?
So can we write y is equal to f of y and then can open that website bracket to cancel out f of y and write down without putting the value.
I will get it. Are we done? We are not. So this is another very dangerous mistake in functional equations called the pointwise trap. What does a pointwise trap mean? See, I proved f of t equal to plus minus t for all t in R. Right. But who prevented f1 equal to 1, f2 equal to minus 2? I can have this, right? If I just eliminate f of t equal to plus minus t for every t in R, for some t's I can put plus, for some t's I can put minus, right? And you see, f of x equal to x, this function is not equal to this function, right? Because fx equal to x puts the same sign for all x. Similarly, fx equal to minus x puts the minus sign for all x. But I can have a function where I put plus for something and minus for others. Right? Who is talking through doing this? So this is the most common source of mistake in Olympiad problems. It's basically people get it here and then they conclude also fx equal to x and fx equal to minus x. Done. It's not true. So the reason this is called a pointwise trap is first of all because it's a trap to reduce marks here. The reason it's called pointwise trap is because I can flip the signs pointwise and get a function which is neither x nor minus x. Right, so I'm not done yet. But luckily we are nearing the end soon. Uh, so this example is really nice because this one example teaches you a lot about functional equations. You learned about involutions, uh, and you also learned about pointwise trap, and you also learned the importance of variable substitutions. So when you have a situation, when you have a pointwise trap, the easiest way to proceed is, the stupidest way to proceed. So first of all, you see that f of t equal to plus minus t. That means that f of 0 equal to 0. So suppose we have two non-zero numbers, a b not equal to 0, such that f of a equal to a and f of b equal to minus b. So suppose we have functions such that which flip the signs in two different tables. What should I do? Put x equal to a, y equal to 0. So what do you get? What is f of a? A. So fx square becomes a square. What is f of y? Minus b. F of b is minus b. So you have a here. What is f of a? And what is y? You have this. Right? So what does this give you? So on the other hand, what is f of a square minus b? Plus minus a square minus b, right? It is either a square minus b or minus of a square minus b. So if it is a square minus b, then what do we have? A square minus b equal to a square plus b, which means b equal to 0. Contradiction, right? We assume that a was anywhere non-zero. And if we have minus of a square minus b equal to a square plus b, what do we have? B minus a square equals b plus a square, which means a square equals 0, which means a is 0. Once again, contradiction because of equal. So now we can finally finish it and say that either ft will have to be t for all r, or it will have to be minus t for all r. It cannot be the case that it is plus t for some t and minus t for other. So this is how you evade the pointwise trap. Is this clear? Also, one last thing. So this is a very silly thing for which students lose marks in Olympiad. Is that they finish this proof and this proof is correct. There is no trap and even this proof is correct and done. So we should just close books and leave the exam, right? one large silly line you have to write is that we verify that f of x equal to x and f of x equal to minus x are indeed solutions to this. Many students forget to write that because that part is usually trivial, verify that. But trivial though it may, you have to verify that. So, uh, so for example, this problem is from the method of Ivan Chev. Ivan Chev was an IMO, three-time IMO expert. He lost 1 mark in the IMO because he solved the entire functional equation correctly. But then he forgot to verify that the solutions that he had gotten were indeed correct. So he forgot to write one trivial thing and that cost him 1 mark out of 7. Basically, it's like because you have done so much work, just that thing that we verify that the solutions we have gotten indeed work. And this verification is also important because sometimes even after all this manipulation, you still manage to retain some spurious solutions. So if you sit down and actually verify that they work, you can, will also save from the possibility that you have accidentally not written some bogus technique. Was this problem clear to all of you? So this is a really silly question and when you see the solution. So the previous question, that question was when you solve it, you get a certain sense of satisfaction. Like, okay, so this was a tough one, but I kept hitting it in 5 minutes ago. This one when I show you, and if you don't get this, feel like got it done. How can you combine it? When did I say that I was additive? Yeah. So anybody has any ideas? Okay, that leads epsilon to 0. After that, see, so when you see an equation like this, so all the equations that you saw before, they're like simple equations. You have some fx and y somewhere. The last one was a bit more complicated, it had some nesting. But here you have x to the power 27, right? Now, normally during when you do algebra, very rarely do you encounter stuff like x to the power 27. So you are not normally multiplying x 27 times to get it. Which means that something fishy is going on. Now, there is a fourth trick of functional equations, which is always aim for cancellations. Now, cancellations can be of many sorts. So, we saw one type of cancellation in the previous question where we had gotten a u such that f of equal to 0. Right? So, we put that u in a strategic position so that it becomes 0 and that kind of period or expression of it. Right? That's what one sort of cancellation. Here we are looking for a different sort of cancellation. Put this and simplify. What do you get? No. How will you compute f of minus 1? What you can conclude is that f is 0 or non-negative. So, when you put this and simplify it, do all of you get this? What does this mean? That if I have any positive real number r, then I can put x equal to 4 root of r, and I will get f r equal to 0. Right? I can put x equal to 4 root of r and I will get f r equal to 0. Am I clear? So what do we get? That f equal to 0, f r equal to 0 if r greater than or equal to 0. So that is a huge help. We have covered half of r basically. We have covered all the positive numbers. But you can still say anything about f of minus 1, right? Because there is no real number x whose fourth power is minus 1. So what do you want to do about minus 1?
We can substitute x as -1 and y as 0. Then we can get f of -1
And
as
how do you get minus 3? Take minus 27 root of 3 and y. Basically, the key insight that he had was that put y equal to 0. Remember, every problem does not involve a new trick. What was one trick that we learned just an hour ago? The first instinct should be to put everything 0. The second instinct should be to put one of the things 0. Which one should we put 0? Y. What do we get? F of x square equal to f of x to the power 27 plus f of x to the power 4. Now see x to the power 4 is x to the power 4 is non-negative, so f of x to the power 4 is 0. X square is non-negative, so f of x square is 0. Which means f of x to the power 27 is 0 for all x in R. And now you are in luck. Because although there does not exist a real number whose fourth power is minus 1, there do exist real numbers whose 27th power is minus 1 itself, right? And even for say minus 5, you can put x equals to minus 27 root of 5 and x to the power 27 minus 5. The key fact here is that 27 is an odd number. So this minus 1 will get exponentiated an odd number of times, then you get minus 1. So if another more fancier way of saying it is that x maps to x to the power 27 is bijective. Or rather, here we only need subjectivity. That is, for every real number x, every real number r, there exists x in R such that x to the power 27 equals R. And this is true even for negative ones. Which means that fx is identically 0. Fx is the constant function z. Was this example clear to all of you? While this is only a 2-hour session and I obviously cannot, give you indefinitely many problems, each of the tricks that I am saying you should write it down and whenever you sit down to solve a functional equation, you should see what all you can do. So the tricks are put x equal to y equal to 0, then put x equal to 0 and keep y alone, or put y equal to 0 and keep x alone. In general, try to manipulate as much as you can and see what you get. Try to get cancellations. If you ever get an involution, then you have a bijective function in your hand. Do not fall into the pointwise trap. If you ever get an expression of the form f of u equal f of something equal to 0, substitute that something to a variable, and then you can substitute that variable in other places to kind of clear expressions up, because it will evaluate to 0. So these are some. So don't just blindly write everything down. Try to make note of these important things. And then there's the importance of shifting. Right. So if you can shift, try to do so, because then you get one value first. The value at 0 you get for free. This thing will involve a very weird shift. From one side you can put 0 and f of 0 is equal to 0. If you put one of the variables with 0, if you put n equal to 0, you get fm equal to fm plus f0 plus 0. f0 is 0, so you get fm equal to fm, so that does not yield anything. Right? Okay, so another thing that you should always keep in mind is that whenever you see a functional equation, even if you're trying to prove anything, try to guess what its solutions are. Right? Now you see the obvious cases like Kn, like fx equal to kx. And by the way, this is our function equation for integers. Now we are not talking about real numbers; these are integers. Fx equal to kx does not work here. You see, because fx equal to kx will get cancelled and then you have to then left. So fx equal to kx does not work. But what does mn remind you of? When you are doing algebra, where might mn arise?
Square.
Square it, right? You see, m plus n is just m plus n, but when you square m plus n, you get m square plus 2mn plus n square. There is this extra 2mn, right? So now that I have given you a hint, produce for me a solution of this function. When you square, you get 2mn. I want just mn, so what should I do?
M plus n square minus n.
Square and divide by 2, right? I mean, instead of suggesting, can you just try whatever you're suggesting and see if it works? Can anyone find a solution?
fx equal to x square by 2.
Exactly. Right. I mean, you get mn when you square stuff, but you get 2mn when you square it. So I want just mn. So x square by 2, and when you put x square by 2, this becomes m square plus 2mn plus n square by 2. This becomes m square by 2. This becomes n square by 2. This becomes mn. Okay, so we found the solution. Now what do we do? First of all, there is still a catch. First of all, x square by 2 is not a solution, strictly speaking. Why? Because it is a function from integers to integers. X square by 2 does not have an integer per integer. So we have 1 to half. But algebraically speaking, x square by 2 is a solution. So, we have made some progress, but first of all, this is not the final answer clearly. And secondly, yes. So basically, he is saying x square minus x by 2. Right. Can you verify why this works? Basically, what happens is that this square term will kill off this element. And in the end, you just have the Cauchy equation left, right? So this x will satisfy that. Just, instead of taking me for my word, just put this and you realize what's going on. And this is a solution. X square minus x by 2 is a solution. Why? Because x square minus x by 2 is always an integer if x is an integer. Right? By the way, if x square minus x by 2 is a solution, why is it x square minus 25x by 2 a solution? When I say this is a solution, I expect that you guys will actually check that. Check that this is a solution. Have you checked that? Is it a solution? Now I want all of you to check that x square plus lambda x by 2 solution for any line. In particular, you get this solution when you put lambda equals -1. But I want you to check that this is a solution. And if you have indeed checked that this is a solution, convincing yourself that this is a solution will take 1 second. Because you see all the x square term will kill off away, and then you will just have Cauchy. So have all of you verified that this is a solution? So once again, this is not a complete solution because my code domain must be an integer, so I cannot clearly have solved like x square plus move to x y. If this was a functional equation over real, I'm not sure, but the code domain must be R. But let's set that aside for a moment. So this is clearly a solution, right? And the reason why I'm repeatedly emphasizing that you should check for yourself that this is indeed a solution is when you check that you will realize that the square terms are killing this term off, and in the end you have Cauchy there, right? Now this is checking that some solution works is one thing, right? But now you have to actually prove. How do you prove something? How do you prove that this is the only class of solutions? So probably, although when I write it, so it's the same thing with most mathematical problems. When I say what the solution is, you'll be like banging your head, but even though everything is right in front of you, it is a bit difficult to see actually what is to be done. What is to be done is shift, that's why you should write it. Set gm equal to fn minus m square by 2. What do you get? Now simplify. What is f of m plus n? G of m plus n plus m square plus 2mn plus n square by 2. What is fn? Gm plus m square by 2. What is fn? Gm plus m square by 2. And you know that. What will you get? Is everyone with me? What do you get?
N by 2 plus n by 2.
You can just cancel this guy. What do you get? G satisfies the Cauchy's equation. And now you see G is a function from Z to So for a moment, let's forget about the code domain. So G is a function from Z to R, right? So because G is a function of Z, we know what the solution of the Cauchy equation is, right? What is it? Gm equal to lambda for any lambda, right? And this is the only possible class of solutions. Gm equal to lambda, right? So if Gm equal to lambda, then what is Fm? M square by 2 plus lambda. Basically M square plus 2 lambda and by 2. So note that you have already proved this. So was this question clear? Was this whole proof clear? We shifted. So the previous examples of shifts that you saw, we shifted to make the input at 0, 0, right? Now we shifted by a different function altogether. Now we are not shifting by f0, we are shifting by x square by 2. Why? Because once you shift by that function, all that annoying term mn gets cancelled off and you get Cauchy. And Cauchy we know how to solve. At least over the integers you know how to solve. So you get fx equal to x square plus lambda x by 2, where lambda is any real number, right? Now you are almost there, but if this was an Olympiad question, if you just write this, you will not get full marks. Why? Because f was a function of z to z, right? The codomain of this function is not, the range of this function is not z for general lambda, right? First of all, it's easy to see that lambda is not an integer. This will produce non-integral values. Why? Lambda is some general constant. So now forget that lambda was some g or something. Lambda is some constant, right? So I'll leave it to you to verify that if lambda is not an integer, this will also not be an integer for some x. But even if lambda is an integer, so suppose we have lambda of 0, x square by 2 is still not an integer for all x, right? So now you say this is x into x plus lambda by 2. Lambda is now an integer. If this has to be an integer, that means that either this or this has to be even, right? So if x is even, fine, but what if x is odd? Then this has to be even. This can only be even if lambda is odd. So the only solutions to this function equation are x into x plus c by 2, where c is an odd integer. This is the final solution. This is what will get you 2 marks. So the main, difficulty in this question was, this very innovative idea of shifting by an entire function. Once you do that, it's Cauchy, and after that, it's just some case handling. If you can make that shift, that will get you 90% of the marks. Remaining this lambda has to be even and all that. It's just some final Cauchy work. But the main takeaway is that you can shift not just by constants but by entire functions. Nobody is stopping you from doing that. But when is shifting useful? Shifting is useful only when shifting kills off some annoying terms and simplifies the function equation. Earlier we used to shift because that used to give us one value for free. Now we shifted because it killed the mn term. Because you see g fm f of n plus n equal to fm plus fn plus mn. This is almost Cauchy, except for this annoying mn term. So it would have been really nice to get rid of this mn term, and indeed we did. And once we got rid of the mn term, f is indeed Cauchy. So, and then you are done. So this one is miscellaneous. So just to clarify, what is n? Yes, what does it say? What is n 0? 0, 1. Okay, so f of n 0 to n 0. F is strictly increasing. F of m plus n equals f of m plus f of n plus fm m n for all n. Find all such functions will satisfy these four properties. So, a TST problem, but once you solve it, you realize it's quite easy. But okay, since you are starting off for the first time, um, so I'll give you some hints. Because so the key to solving functional equations is just manipulating, right? But here there is not much you can do. But when you are not sure what you have to do, just put in values and check what you do. That won't happen. Just calculate F4 and F8. Just do this much. What's the value of F4?
3.
Very good. What's the value of F8? You have to just put mn equal to 4, right? You get F8. What's F8?
4095.
No, I think you made a mistake. First of all, how can it be F8 can't be a power.
335.
Right. Plus Z equal to the uh, just a second. No, powers of 2 is not the answer. Okay, I think there's been a lot of confusion. I'll just tell you one thing. Put gx equal to fx plus 1. Apply this shift and see what this equation becomes. Just apply this equation and see what you get. What do you get? Apply this shift and see what you get. What do you get? This becomes g of mn n plus n minus 1. This becomes gn minus 1, gn minus 1 plus gn minus 1 into gn minus 1, which becomes g of mn. So g of m g of n minus g of n minus g of n plus 1. What do you get? Wait. I miswrote the answer. That does not change the shift. Sorry, miswrote the equation. So you get g of mn plus g of n g of n. And now you see what's g of 2? What's g of 4? And now it makes sense. What is g of 8? G of 4 into g of 2, right? What's g of 4? And g of 4 is formula g of 2 into g of 2. This becomes g2 cube. What is g2? 8. So do you see a pattern here? What's the pattern? Cubes, right? 2 cube 8, 4 cube 64, 8 cube cubes, right? The reason, so many people got confused between powers of 2. So while I apologize for the miswriting, the only reason we are getting powers of 2 is because I have given you the value of f2, right? You can never get something like 6 because where will you get a 3 from? That's why we are only dealing with powers of 2. But the answer is not 2 powers something. The answer is cubing. G of 2 becomes 8. G of 4 becomes 64. G of 8 becomes 8 cube. So now our new question is find all strictly increasing G such that G of 2 is 8 and G of mn is G of G. So this is our new question. So this is another example of shift. And how could you have seen the shift coming? Like how do you guess that we have to do a shift here? Because you see what the original equation was fn plus fm into fn. So you see when you have things like x plus 1 into y plus 1 or x minus 1 into y minus 1, when you have things like this, you will get an xy term. And so why did we choose fn plus 1? So basically f is g minus 1. Why did we choose g minus 1 and not g plus 1? Because when you choose terms to be minus 1, there is a chance of cancellations available. If you choose f equal to g plus 1, nothing will ever cancel because everything will add up, right? We want this fn term to go up. We want some cancellations. So that's why we will put g f equal to g minus 1. So then fn will become gn minus 1, fn will become gn minus 1, and you see indeed all the cancellations occur and you get this. So can you prove using induction that g of 2 to the power k is 2 to the power 3k or k greater than 1? So can you prove this? It is very easy to prove, right? I mean, first of all, g1 is easy to calculate now because gn equal to gn into g1, so and g2 is now 0, so you can cancel it. So g1 becomes 1. G2 is 0. How do you calculate g4? G4 is g2 square. Equal to cube square, 2 square, cube, 4 cube. How do you calculate g8? G8 is g4, g2. Is 4 cube, 2 cube, 8 cube. But how do you calculate 16? G8, g2, 8 cube, 2 cube, 16. So g of 2 to the power k becomes 2 to the power 3k for all k greater than equal to 6. Right. Now what do we want to prove? That g of x equal to x cube for all integers x, for all natural numbers x, right? But so far we have only gotten the powers of 2. How do we proceed? This is all we know right now, right? And we also know that g of 2 to the power k is k to the power. This is all. Now, how do I extend this to all of integers? So these are not, you can try this on your own, but this is a very specific trick. So actually, this is a trick from calculus. This does not involve any calculus, but when you go to college, you will see this sort of trick appearing in calculus often. So the thing is that f g is strictly increasing, right? So g is a function like this, and we have gotten its values in at powers of 2, right? But what is preventing it from doing something like this? I mean, this is also strictly increasing, right? This function is also strictly increasing, right? And it matches, but at other values it's not excluded. So how do you rule out functions like this? Did all of you get what the problem is? That we have the values at the powers of 2, but outside the powers of 2 it may not necessarily be n cube, right? How do you force that it is n cube for all? So here the trick is that first of all the function is strictly increasing. Secondly, it's completely multiplicative. So I will not ask suggestions on this because this is a bit hard to guess. So suppose there is some n such that gn greater than or equal to n cube plus 1. So for which gn is greater than n cube. See, if gn is not equal to n cube, then it has to be greater than n cube or less than n cube. Right? So we assume it's greater than n cube. The less than n cube case is analogous. to be a rational number such that n cube less than 2 to the power alpha less than n cube plus 1. Why can we do this? Basically, see if I take log to the base 2, you get 3 log 2n less than alpha is then 3 log 2 up to n cube plus 1. This is a real number, this is a real number. And you can always find a rational number between two real numbers. You know this, right? You can always find a rational number between two real numbers. So find such a rational number. For that rational number, you will have this. Right. Now, why do I want some weird rational number like this? Now I basically say alpha equal to p by q and do Cauchy. Like is this visible to all of you? Do you understand what I did? Basically, I took an rational number alpha such that n cube less than 2 to the power alpha less than n cube plus 1. I now exponentiate to alpha to make everything integer. N to the power 3 cube less than 2 to the power p less than n cube plus 1 to the power cube. Right. Now, what is g of n to the power 3 cube? It is g of n to the power 3 cube because g is multiplicative, right? Because and now n to the power 3 is less than 2 to the power p. G is strictly increasing. So g of n to the power 3q is less than g of 2 to the power p. G of 2 to the power p is 2 to the power 3p. So gn to the power 3q is less than 2 to the power 3p, which implies that gn is less than 2 to the power p by q. 2 to the power p by q was less than n cube plus 1 by assumption. But we have assumed that gn was greater than equal to n cube plus 1. So contradiction. So note this thing down. So this is an advanced technique. But so that's all I have to cover for functional relations. If you have any doubts?
Now I would like to thank Dr. Basu sir. He explained us complex topics like polynomials and functions in a simple manner and an interactive manner. Thank you, sir. And you opened us opportunities to learn these topics further. Thank you.